So very good evening class. So we are going to continue with chapter 6. We are done with chapter 4, which is actually on subroutine. And we're going to go to chapter 6. And then from there we'll go to chapter 8. And we'll go something more. So for the Tuesday night class, this week will be the last one.
Why is it? No, 61.
This week will be the last Tuesday class. Because next Tuesday I cannot make it. Hey, the other two is not a week, right? But no need.
Why not?
Okay, we'll see how it is. See how. That's Sasi with his pom-pom is doing. Sasi, were you in the cheerleaders team? Huh? Were you in the cheerleader team? The expression is good. So tomorrow we'll have, because next week, Tuesday I can't make it. The following week, we'll see how. Let's see how. If we cannot finish, then we'll do. Okay, let's start with chapter 6. So chapter 6 is about interrupt. Now chapter 6 and this chapter 6 and chapter 7 and chapter 8 will always consist of question number 3 and question number 4 the final examination. Now by this time you all can actually download the past year paper. Last semester. See, I only have last semester because I came after study leave last semester. The previous one, I think you can. I think library they also have, right? They own archive. Library should have, right? Okay, tell you what. Don't expect the answer because there are no answers. You see how the final questions have been said. It's been said in such a way that there cannot be a specific way to answer. See, this is a programming language, except for theoretical questions or the calculation. I mean, this particular way to do it, then that's how it should be done. But for the most of the part, if you get the answer scheme also, you say initialize timer. How you initialize timer? There's few steps, but depends on which timer that you want to choose. Initialize or configure your interrupt. Which interrupt? Depends on which interrupt you choose. So don't expect for the answer. That's my. Any other question? Anyway, you should be able to do that. Not a problem. I think.
Also, thank you for the confidence.
I'll know when you do test 2, I'll know already your level. That time I will know your level. Whether you can do or cannot do. Anyway, let's start with our topic which is on interrupt. So in our previous chapter, we actually have done on subroutine. Now, how do we actually call a subroutine? Call. We use call, then we call the subroutine. Now, what is the component of the subroutine? Must have the name of the subroutine and must have the content and then return. We also saw the examples if we need to save, right, some important CPU registers. Either we use the fast register stack or any other register besides the fast register stack. We can actually use push and pop to store those values in the stack. We also have seen the concept of stack. We have done the concept of stack as well and how to use the stack to store temporarily and also to retrieve back those information. Right? Now we're going to go to chapter 6, which is interrupt. Now in interrupt, we are also going to use subroutine. It's called as interrupt service subroutine. ISR, interrupt service subroutine. Interrupt service routine. Sorry. dealing with subroutine, what is known as an interrupt service routine. Now, compared to, that's why we actually we follow the flow. We actually learn about subroutine and then only we go to chapter 6 because it's also using the concept of subroutine. But the thing is, the difference is, here in this chapter, we configure the interrupt or the subroutine. And we have the subroutine in our program. After the main program, we'll have the subroutine. But the subroutine won't be called, we won't call the subroutine in the main program. It actually will be called by an interrupt. You have to configure an interrupt. Of course, I'm just giving you the concept. Later, you'll understand later anyway. You have to configure an interrupt source. When the interrupt is triggered, automatically that subroutine will be called. It's not that in the program you write call the subroutine. No. You have to configure an interrupt. When the interrupt is triggered, that subroutine will be called. Compared to previously, in chapter 4, what we learned, how to call subroutine, we as the user, we have to define when do we call the subroutine in the program, right? That's actually in the software level, we actually write call, when we actually call the subroutine. But in the interrupt, not like that. You just configure the interrupt and you just leave it. The main program will continue to run. When the interrupt happens, the main program will stop, and immediately from the main program it will go to the subroutine. Now, very simple real life application would be your traffic light. Now, if you see a traffic light, crossroad traffic light which has a pedestrian cross, imagine the sequence of the traffic lights which are changing continuously are like the flow of your main program. Right? If no one is interrupting the pedestrian cross button, the main program will continue to run, right? So only when someone presses the button, someone is actually interrupting the main program. When you press the button, there is another subroutine to run this pedestrian crossing for the code and the light or whatever blinking. There's another program. That program is actually, imagine that like your subroutine, interrupt service subroutine. So when you press the button, the interrupt is being triggered. Signal is sent to the main program to stop and then to go to the interrupt service subroutine, whereby what will happen, it will make sure that all the lights are all red, then it actually turn on the green for the pedestrian to cross. You able to get the concept? I just want you to understand the concept. Later you'll see in terms of implementation, how can we implement that. Then after the pedestrian thing is finished, what happens? It returns back to the main program and runs back like normal. So that's how the concept of interrupt is. Or another simple analogy is, like let's say you are doing some assignment in your apartment, then suddenly you receive a phone call. What do? You stop your work, you take the phone call, you answer. Of course, what we tend to do, we'll answer and forget the assignment. By assuming that the phone call was a missed call or a wrong call or a wrong number. Don't lie, wrong number, then 1 hour. Then what you do after answering the call, you come back and continue your work, right? So whatever work you're doing is akin to your main program. And whatever the phone answering is like the interrupt request, you do another task. So the other task is actually in the subroutine. But how the subroutine is called is when the interrupt is triggered. Only when the interrupt is triggered. Do you understand the concept? That's how interrupt is. So we'll see some of the concepts of interrupts. Interrupt is one of the very, very, very most important application in the real time. And it is very, very useful because of its prompt response. Very, very useful. Remember earlier in chapter 7 we saw that there's two ways of interfacing. One is polling and one is through interrupt. So interrupt is way, way better. Maybe in one of the examples we shall see. So let's see. So without interrupt, the processor will execute program by following the program logic flow. That means if you have something to do in the main program like the traffic light, that's the main program to keep rotating the traffic light flow. If no one giving any interrupt for the pedestrian cross, the main program will just keep on running by itself. So interrupt is an event that will cause the CPU to stop the normal program execution and provide some service to the event. Can you relate to the traffic light pedestrian crossing thing? An interrupt can be generated inside or outside the microcontroller chip. Now this is the thing. The interrupt, there's interrupt source within the microcontroller. There is also, you can also use external interrupt to crossing. So an example of inside interrupt means inside microcontroller there are timer. Timer is our next chapter we're going to learn. So you can actually configure the timer. For example, you have your microwave oven. You can actually set a particular time. What it does, it actually counts down, right? It counts down. When the time is finished, there is a beep or some bell sound indicating end of time. So you can also do the same thing here. For example, okay, you have learned how to actually interface with LED. Let's say you make interfacing of LEDs, port, whatever port. And then what you do is you configure the internal timer to actually set the timer for every 1 second, for example. So at every 1 second, you can actually configure the timer. At the end of the 1 second, you can make it as an interrupt, and that interrupt will actually call the subroutine. And what you can do in the subroutine is, for example, you can actually, maybe you can alternate the LED to turn on and off every 1 second. So that interrupt, whenever the timer finishes, that end of time will generate the interrupt, and that interrupt will call the subroutine, which will alternate the port. So that's one example of internal interrupt. External interrupt is in port B, all the pins in port B, you can also use them as interrupt. We shall see later. That means you can connect to a switch. So whenever you press the switch, just like the pedestrian cross, it's like a switch, right? That's external. It's not from inside microcontroller. It's outside. You can also connect to a switch. When you press the switch, then only it will generate the interrupt, and that interrupt will call the subroutine. So it is not inside the program we are calling the subroutine. It is something from which generates the interrupt. Now what can generate interrupt? It could be the internal timer, or it could be the external switch. Whatever you press, that will actually call the subroutine, not the call function. Okay? Any question up to this point? I know first of all you don't even understand yet. From an example you see that. And internal, okay, did I so I mentioned. Okay. So there's a lot of applications of interrupt. Now, the interrupt, as I mentioned, there's a lot of interrupt that can be generated, and sometimes you can have more than one interrupt at a time. So when more than one interrupt happen at a time, you can actually program in a way to give priority to which interrupt. So let's say in the traffic light, there are more than one pedestrian cross, right? There are two pedestrians press the button at the same time, which is impossible to happen, assuming they press at the same time. So which one you want to execute first? It's up to us. You can give priority to which one. Assuming that both press at the same time, you can give priority to this one. Decide first. Then you do the one. So like that you can actually choose. I just want you to know that there is some such thing known as the priority scheme. We have the priority. How are we going to do that? We'll see later. So we have two levels of priority. This is what I mentioned. A microcontroller normally has multiple interrupt sources. That means you can have multiple interrupt sources coming in at the same time. More than one interrupt source can be pending at the same time. The CPU needs to decide which one of the pending interrupts to service. Which one to attend to. The solution is to prioritize all interrupts. That means every time it happens, you prioritize this is the higher or this is lower. So there are two levels of priority. One is high priority and another one is low. We have two levels of priority. So whenever the interrupt happens, how it actually works. More or less, if you see the step, it is something like when you call the subroutine in the program. So the CPU provides service to an interrupt by executing an interrupt service routine. After providing the service to the pending interrupt, the CPU must resume normal program execution. This is exactly same like in the previous chapter where we actually call the subroutine. When you call the subroutine and after this finish, you come back to the main program and continue back, right? Same thing here. So the complete interrupt service cycle involves the following. So first thing, whenever the interrupt is being triggered, what happens is it saves the program counter in the stack. Which stack? The return address stack. So this is as if you are calling the subroutine. So it will save the CPU status automatically for interrupt. It will identify the interrupt source. That means which address is to go for the interrupt service routine. And it will resolve the starting address of the corresponding interrupt service routine. Now, identifying the interrupt source, there are actually two levels of interrupt source, we shall see later. Remember, in your program start template, you have that origin hex 08 and hex 1818. Those are the two addresses for the corresponding interrupt service routine. The top one is high, the down one is low. So those are fixed addresses. And then you execute the interrupt service routine. It means you execute the routine. After you're done, what happens? You return back, you restore back the CPU status from the stack, you restore back the program counter from the stack, resume back to the main program. This is the same like how we used to do for the chapter 4, right? When we call the subroutine. Is it okay? Later also when we do the example, I'll explain the same thing better. So there is one term known as the interrupt vector. So I think this was one of the most popular questions they used to ask, and students always don't answer this. It's one of the easiest things. Interrupt vector means it's the starting address of the interrupt service routine. That is interrupt vector. It is very, very simple. So there are three methods of determining the interrupt vector. In our case, it's already predefined. Remember this origin 08 and also 18. This is actually the interrupt vector for high priority interrupt. This is the interrupt vector for low priority interrupt. Why I'm not spending much time explaining that is because if I explain also you won't understand. And I want to explain certain things, and straight away when you go do the examples, then you can see the bigger picture. Is it okay? Now I keep mentioning about interrupt. What are the interrupt sources? Interrupt sources means what can actually cause the interrupt. So we're going to go and see now what are the pins which can actually be the interrupt source. So what are the sources that we have? We have 4 edge-triggered interrupt pins. IT0, 1, 2, 3 interrupts. Now this pins is IT0 is actually pin RB0. RB0, RB1, RB2, RB3. Each one of them, you can actually configure them as edge-triggered. That means you can trigger them by high or you can trigger them by low pass. And then port B pins change. Just now I mentioned port B pin 0, 1, 2, 3, they are actually interrupt 0, 1, 2, 3. And then there is pin 4, 5, 6, 7, right? Those are categorized under port B pins change. And then there is also on-chip peripheral functions interrupt. One of it is like the timer, ADC module, and so many other things like that. So all this can actually can be used as an interrupt source. You'll see all this in a matter. So what are the registers related to interrupts? Because now we have the interrupt source. So we need to actually configure them. Then only it can actually work. So for that we need to know what are the registers actually related to the interrupts. So these registers are related to interrupts. So you need to know how to find these values inside these registers. Now what is inside these registers? Basically what you want to do is, you want to do this. Every interrupt source has 3 bits. They are known as the control bits to control its operation. It consists of a flag bit, consists of enable bit, and consists of a priority bit. Our aim is to configure these 3 bits. That's what we are going to do. Okay, time for example. You can see things better. Okay, this is the example that we're going to try to do now. Configure interrupt 1 to high priority and enable this interrupt. It's just this one, you're just supposed to write the instruction sequence to configure interrupt 1 to high priority and enable this interrupt. Now interrupt 1 is actually pin number RB1, pin number 1 of port P. Now when you see the schematic, you can see something like this, RB1/INT1. Remember in chapter 7, we saw that one pin can have more than one function. So this pin, what it means that this particular pin, pin 1 of port P, you can use it as a normal input-output pin, or you can use it as interrupt. So this one means normal digital input-output. This is used as interrupt. If you want to use this as a normal input-output pin, what should we do? To configure it?
Configure. Yes.
We configure the trees, right?
Yes, set trees.
Because trees is for digital input-output pins. Now, the question says, use this pin as interrupt. That means now this pin is going to become interrupt source. So here why I just draw the schematic, to show, give you an idea that this, when you press the switch, it will actually cause change of logic, right? That change of logic will actually make the flag bit 1. When the flag bit 1, when the flag bit becomes 1, that indicates that the interrupt has occurred. And what happens? Immediately, the main program will stop and it will call the subroutine. Is it okay? That's the idea. Later, when we do the full program, you can see the whole flow. I'm just drawing this so that you can see some idea. So, given something like this, so first thing what you should do is, you should first identify the interrupt source. You should identify the interrupt source. So from this one, which is interrupt source? Which one is interrupt source? Whenever you see some short abbreviation that you don't understand, most likely that will be the interrupt source. This one. This is your interrupt source, right? INT1. Don't worry about writing. Understand. Later you can write. First you have to identify the interrupt source. Then why we actually want to identify the interrupt source? Because the second step is you have to identify the interrupt group. There is only two groups. One is the core group, one is the peripheral group. Now the core group consists of this INT0, INT1, INT2, INT3, RB change, which is actually port B, pin number 4 until pin number 7, and also timer 0. Right, timer 0, right? The slides, what's mentioned? So count number. Very golden nowadays. Interrupt source, all this actually interrupt source, all this, only this interrupt source belongs to core group. That means INT0, INT1, INT2, INT3, then port B change, and also timer 0. Only this interrupt source belongs to core group. Any other abbreviation that you see besides this, it falls under peripheral group. Is that easy? Okay or not okay? So once you have identified, so now what is our interrupt source? What is our interrupt source? Interrupt 1, right? Second step, it belongs to which group? Core group. Why we want to identify the cog group is because note that our aim is to configure these 3 bits. What these 3 bits do to its interrupt source, I'll explain in a while. We want to configure these 3 bits. Okay, I'll just explain now. The flag bit. The flag bit is actually the indicator whether interrupt has happened or not. So usually whenever you want to enable the interrupt, you must make sure that the flag bit is cleared so that when the interrupt happens, the flag becomes 1. When the flag becomes 1, it indicates that interrupt has happened. That's what it means. That's why we have the flag bit. So whenever we want to configure, we want to make this 0. Because 1 means it means the interrupt has happened. And then you have enable bit. Enable bit means you have to turn it on. If you don't enable it, the interrupt won't work. And then the third one is priority bit. Whether you want to set to high priority or low priority. So these 3 things we want to configure. And where are these 3 things? For the cog groups, these 3 bits contain somewhere here. It's mixed up. Somewhere you have to find. And for the peripheral, it is more organized. All these registers only contains priority bits. All these registers only contain enable. All this contains flag. Okay, I wrote it wrongly. This is priority. It's flag. Is it okay? Yes. So the third step is you're supposed to enable the priority scheme. Put here always because this tab it always will be there in any interrupt configuration. So where is actually the priority enable thing? It's actually in RCON. It's in RCON. So can you view RCON? Yeah, go to your slide C, RCON. This is the RCON register. In the RCON register, there are a lot of bits, right? See bit number 7. The bit number 7 has a name, IPAN. What is it mentioned? Interrupt priority enable bit. If it's 0 means disable priority levels. If it's 1 means enable priority level. So you want to disable or enable? So you want to enable. So how do you enable it? Bit set F. What is the register name? RCON. What is the bit name? Either IPAN or you can put 7. This is a bit oriented instruction, right? This is F, B and A. You remember? This is F, this is B, this is A. F will be because all these are special function registers. Tell you the name. This is actually the bit position. Now in this case, even the bit got name. The bit number 7 name is IPAN. So, okay, don't put bit pen. Either you write here IPAN or you can put 7. This chapter 6 you will see bits also have names. Special dedicated names. You okay? So this is the first line. Enable the priority scheme. Always that's the line. That's a fixed line. Enable priority scheme is the one. That's it. Then the next step is we need to configure the 3 control bits. Now because we have identified that this interrupt source belongs in the core group, we should go and find for these 3 bits in the core group. So let's say we want to configure the flag bit first. So what you need to do is the flag bit will be somewhere between inside these 3 registers. You just have to find out where. So let's see incon. So let's go to the first register, which is incon. This is actually incon, which you cannot see now. Cannot stop halfway. I tried to. Okay. He stopped and he went up back. I didn't do anything. He went up back. Okay, now our aim is to find out, to configure the flag bit of interrupt 1. So we need to find for interrupt 1 flag bit. So how do you actually find for the flag bit? It's quite easy. It always you have the interrupt source, right? Our interrupt source is interrupt 1. The flag always will have interrupt flag. Search for the bit. Do you have any bit like that? Yes. But there's ID 0. So let's. Okay, search don't have, right? That's why I say this one you have to go search. Indiana Jones. So look for the second one. This one is interrupt incon 2. Is it in somewhere in incon 2? No, don't have. Go to incon 3. Is it incon 3? Yeah. Yes, here right. So what do you need to do with this flag bit? Huh? Set or clear? Set. Yeah, just go right. Flag it must always clear. Was always clear. So here you clear. This is interrupt 1 flag. Sorry. What is the name of the bit? This is supposed to be incon 3. The back. Sorry, there's going to be a lot of screen up and down. Okay. Always should have the register name and then the flag. So what do you do this? This one clears the flag. Always you must clear the flag. This one you must always bit clear F. Enable bit must always be set F. Priority, if low priority means bit clear F. If high priority means bit set F. Very easy, right? So we are done with the flag. The next one is, maybe let's try to do the priority because we want to keep the enable last or whichever way. You want to enable first? You can just do enable. So now you have to find for interrupt 1, enable. So what do you think the last 2 letters will be? What do you think the last 2 letters will be? IE. So is there IE there? Bit number? Yes, bit number 3. So what do you have to do with that? Clear or set? After writing someone can set turn it on. What's the last circuit? Priority. This one high priority or low priority? How you know? Yes, mention here. Enable, we just enabled it. So it's the high priority. High priority is set or? Yes, it's set. It's set F. So what do you think this one will come? The last one. Then it. Then you mistake. Is it okay?
So why we set only one F?
Come again?
Why we set one P?
Because we want to set the priority as high priority.
Then the one E is because
Enable. Any other question? So when you do this, your interrupt will still not work. You press the button, still the interrupt won't work. So you have enabled here. The reason is, for high priority interrupts, there are two levels of enable. The fifth one is you have to set the global enable bit or bits. So we are actually dealing with high priority. High priority have two levels of enable. Just now what we did is, this is known as the local enable. Local means that interrupt source enable bit is known as the local enable bit. You also need to enable the global. So there is two levels. So where is actually the global? See this one. This bit is labeled as GIE/GIEH, which means global interrupt enable bit. GIE is global enable interrupt bit. And it has two options, when IPAN equals to 0, when IPAN equals to 1. Ours is
1.
Always IPAN equals to 1. Ours is always this. So when IPAN equals to 1, what it mentions here? Enables all high priority interrupts. Now take note that it also means plus all it enables all high priority interrupts and all interrupts. which means this one, GIE, you have to, that is actually the global interrupt enable. It enables all interrupt. At the same time, it also enables all high priority interrupt. So that's why I'm just making the sentence complete. It enables all interrupt and it also enables high priority interrupt. So that's the two level of enable. We have already enabled the local one, but still it won't work because we need to complete those two levels for high priority now because we are dealing in high priority, right? So high priority has two levels. So what we must do? The last one. We must bit set or bit clear. Yes, you must set. So you must bit set. So this one is in con. So to write GIE or GIEH, we actually can write GIEH. It makes more sense. Why? Because we want to enable global all and also we want to enable high. Of course, if you write GIE also still it will work. GIE means just enabling the global one. But when you write GIEH, it makes more sense. So now the interrupt is active. Now the interrupt is active. So now when you press the button, yes, the interrupt can be called. Is it okay? How can we call? We'll see later. Is it okay? Any questions so far? If you don't have a question, I will ask question. You have questions or not? This is very important to understand the interrupt because always you have question 3 and question 4. And in my personal opinion, always you get a lot of marks in those questions. But that's where students will get these marks. No questions? Okay, I have a question. So I have a question. Listen to the question. Can I write this in a different order? That means I put this one up, put this one down, put this one, I can change the order. Can I change the order?
The last 3 lines can. Except
Can change the order. Any order.
except the top one is
Order means this one. Now I have written in this sequence. Can I just juggle it up? Put this one here, put this one down, put that one here. Can or cannot? Either one can. Either one can.
Only alcohol cannot be.
This one always you pick the first one. Is this for?
can.
Can, anyhow also. Actually this for anyhow also can. But the last line should be any one of the enable bits. The last line should be any one of the enable bits. Could be either global or local. Because let's say assuming that in between how you put also doesn't matter. Because the interrupt starts working from here after the second enable. So let's say you enable global first, the interrupt still won't work because the local one still not enabled yet. So last one enable local, then only it works. So the last line should always be the enable. In between you can check it up however you want. Is it okay? Any questions? Questions? Yes or no?
What is global?
What is?
The global and local.
What is global and local? I just explained it just now. Local enable interrupt is, for example, this is the interrupt source. This interrupts, every interrupt source has 3 control bits. One of the control bits is actually enable bit. Then each respective interrupt source's enable bit is known as the local enable bit. Do you understand that? Each interrupt source has a enable bit. That enable bit belongs to that interrupt source. So that because it's only tied to that interrupt source, that enable bit is known as the local enable bit. You understand? And then that is this global enable bit. Global enable bit, you have to turn it on so that all the locals interrupt will work. Is it okay? Any other question?
So, what's the timer for?
What is?
What's the timer for? Previously you said
What,
that TMR0.
This is timer 0.
What's it for?
What I'm trying to say is timer 0 belongs to core group. We have 4 timers. Timer 0, 1, 2, 3, 4. Timer 1, 2, 3 and 4 goes under peripheral group. Timer is used as a timer. We'll see in chapter 8.